Thank you to The Economist for supporting PBS. The tardigrade, the water bear, the moss piglet, capable of surviving extreme drying, freezing, heat, radiation, the vacuum of space, maybe even asteroid impact. And who knows, maybe some tardigrades have hitchhiked on impact ejecta to Mars. And, according to a new study, the tardigrade can survive most of the ravages of the Martian surface. Most. When these researchers tried adding a chemical that is both abundant on Mars and horrifically toxic, even the tardigrade wound down. So, if Earth's most intrepid extremophile can't handle the hostility of the red planet, can anything? Well, maybe yes, maybe even today. Let's see where Martian life and tardigrade astronauts may still be hiding. We've got a couple of quick announcements before we start. First, our eternal battle against the algorithm continues. The best way to encourage YouTube to share our videos is to like and comment. Doing both really makes a difference. And if you're new here, subscribe, hit the bell, and introduce yourself in the comments. We're friendly. Next up, we're excited to launch our Black Hole Light Curves desktop and gaming mat. This NASA-inspired 32 by 16 inch mat accurately highlights the ways light is warped by the gravity of a black hole. The colours are there to help you interpret how light paths are affected by the black hole. There's more info on the merch store site. Plus, our UV Glow Kerr, rotating black hole hoodies, and shirt, plus the dark energy mugs, are all still available. Links in the description. Now, onto the episode. There are a few discoveries that will change everything if and when we make them, but one of the biggest is extraterrestrial life. That's why Mars has been such a focus for NASA's exploration of the solar system. It was once so much like the Earth, a real atmosphere, liquid water on the surface. For a while, we thought we might find primitive life cling to existence on that surface. This was buoyed by Viking landers' labelled release experiment, which tentatively detected metabolic byproducts in Martian soil. But NASA ultimately concluded that this was due to abiotic soil chemistry, and as the inhospitability of the Martian surface became clearer, we downgraded our hopes. For some time now, we've mostly been focused on our searches for signs of past life. And just last year, the Perseverance rover found the most tantalizing such sign in the Jezero crater, mineral composition and patterning that closely resembles the metabolic byproducts of certain Earth microbes. And yes, we did cover that. This potential biosignature is not conclusive, yet it's extremely exciting. Although maybe exciting is now a relative term, relative to our diminishing hope of finding actual living life on Mars. Now, don't get me wrong, signs of past life would be huge, but what if we're not ready to give up? Maybe the Jezero crater discovery should raise our hopes that somewhere the descendants of whatever left those marks are still there, somehow eluding our best efforts. If so, where might they be? There are at least a few regions on Mars that could host some sort of ecosystem, so let's find them. First up, let's review why Mars used to be an oasis and why it's now a hellhole. A wealth of evidence from minerals that only form in water to actual dried river and lake beds showed that liquid water was once abundant on the Martian surface. We also know that Mars once had a much thicker atmosphere. Back in the day, Mars also probably had a magnetic field, powered as with Earth by a natural dynamo, a solid iron core spinning within a molten envelope, but Mars is a lot smaller than Earth, and it shed its smaller reservoir of heat more quickly. The core solidified, the magnetic field shut off, and the Martian atmosphere was exposed to the ablative effect of the solar wind. As that atmosphere was sheared away, temperatures dropped, more atmospheric gases were frozen into the surface, as was the water. We see that water now in Martian ice caps, and it seems occasionally leaking up from a warmer interior. But the surface of Mars is now bone dry, with an asphyxiatingly thin atmosphere that leaves it exposed to intense solar ultraviolet radiation and cosmic rays. But it's even worse than that. The exposed surface is almost all regolith, dust, sand and rock fragments built up from billions of years of meteorite impacts amplified by weathering and erosion, and with no tectonic activity to recycle this stuff. Baking under hard UV, this regolith is photochemically altered into various salts of chlorine and sulfur, but without that tectonic recycling or dissolution by water, these just build up and up and up. Now, many of them, like the perchlorates, are extremely oxidizing and generally bad news for delicate creatures made from organic molecules. Long story short, the Martian surface sucks. If we're searching for extant life on Mars, we need places that are the bullseye of a habitability Venn diagram. Now, Earth boasts some species that are tolerant of some pretty extreme circumstances, so we don't need to be too prescriptive here. But there are some basic conditions that are going to be necessary for any life. First, we need liquid water. Now, persistent large bodies of water may not exist, so we'll need to get creative there. Second, we need protection from all that super bad stuff that Mars tries to inflict on life, like the extreme UV and the cosmic rays, the toxic chemicals at the surface, and the extreme temperature swings. Third, we need some source of energy. Now, for most life on Earth, that's ultimately the sun. But on Mars, direct exposure to the sun means exposure to all of the bad things, so we need to get creative here too. So, we want to come up with a mission to search for where these non-negotiables actually overlap. Water, protection, energy. The easiest way to deal with the protection issue is to get below the surface, and essentially all of our possible habitats will be subterranean or sub-Martian-ian. The less we have to dig, the sooner we'll be able to engineer our mission, so let's start as close to the surface as possible. In fact, we only need to go down a few centimeters into the Martian surface to dramatically reduce ultraviolet radiation, and a few tens of centimeters to give some buffer from temperature swings. This doesn't fix the other major problems of the surface. At these depths, it's always still below the freezing point of water, and we do need liquid water. And the hazardous Martian salts remain extremely abundant. But strangely, it turns out that those same salts may solve the freezing problem. Salts like perchlorates are highly oxidizing, but they're also hygroscopic, meaning they can absorb water vapor directly from the atmosphere, like those little packets of silica. They're also powerful antifreeze agents, allowing the accumulated water to remain a liquid at temperatures as low as -70 Celsius. Under the right temperature and humidity conditions, these salts can deliquesce. They form thin films of brine around particles and within gaps of the Martian regolith. These would likely form in the Martian night and then evaporate in the day. So you could imagine primitive life forms that go into stasis, perhaps even dehydrating to avoid the most dangerous oxidation when the UV is high. But at night, they'd activate, metabolizing the chemical gradients in the Martian soil. Are such organisms even plausible? Well, actually, yeah. We have things on Earth that do some of the required things. There are various halophilic or salt-loving microbes, some of which even use perchlorates as a key part of their metabolic cycle. For microbes in the Martian regolith, the sun would be the ultimate source of energy. For example, a perchlorate metabolizing critter will eat those molecules during the night, while the sun's UV will replenish them during the day. And this points to a question that we can address without even going to Mars. How would the hardiest Earth microbes fare in simulated Martian conditions? It's not that hard to fake the Martian surface. Ultraviolet radiation, low pressure CO2 atmosphere, cold, and a regolith-like soil containing a variety of these salts. Now, I already mentioned the recent tardigrade study. These things do pretty well until perchlorates are introduced. Then they really suffer. And in a 2024 study, halophilic bacteria and fungi were found to survive pretty well in Mars-like regolith conditions, especially at several centimeters depth. But again, this was only until the perchlorates were introduced. Then everything died. So on the one hand, perchlorates may be the best of the Martian salts at forming brines. They suck in more water, and more critically, they suppress the freezing point below the actual Martian surface temperature. But on the other hand, they're lethal. But don't underestimate the ingenuity of life. Even here on Earth, we have microbes that can use those perchlorates as a key part of their metabolism, and on Mars, that could keep the abundance of this stuff in check. And a study just last year found that when you expose E. coli to increasing perchlorate concentrations, they activate pathways for DNA repair and stress mitigation, showing that there are biological solutions to the perchlorate toxicity. On Mars, these perchlorates built up relatively slowly, over billions of years, and so it's plausible that microbe species there have evolved to withstand and even utilize this stuff. So, life could exist at shallow depths in the Martian regolith, even if it's a marginal and tortured existence. But the upside is that this stuff is the easiest to search for, and because of that, our putative life-finding missions are already underway. The Rosalind Franklin rover, now targeted for a 2028 launch, is designed with a 2-meter drill that'll get to depths where cosmic ray protection is good enough even for humans. The mission is focused on looking for signs of past life, but it's possible it'll detect biomarkers in the samples that it draws up. It could even be that the Perseverance rover has already dug up life-bearing material from shallower depths and packaged it for return to Earth. Now, that sample return mission is now in question due to budgetary chaos, but if we can get it to a proper lab on Earth and take a look for all of the biosignatures, even the subtlest or sparsest ones that our Mars robots haven't been able to catch, could be found. Okay, let's see if we can find slightly more hospitable habitats. Mars has widespread near-surface ground ice, especially at high latitudes. And orbital data suggests buried ice deposits at mid-latitudes too. This ice would solve our protection issues. Water in solid or liquid form is a fantastic UV and cosmic ray shield. A meter of it is a common shielding plan for speculative human space missions. And that same UV blocking power and separation from the atmosphere slows the chemistry that leads to the formation of perchlorates, which is probably a good thing. In either phase, water has wonderful temperature stability, which means the layer below this surface ice is protected from the wild temperature fluctuations on the surface. Now, solid water is not liquid water, which is what we really want. But a 2024 NASA study found that meltwater might occasionally form beneath the ground ice. Now, these would be thin layers of water that are warmed from below by weak geothermal energy and from above by the UV-depleted sunlight that filters through the ice. That liquid phase is also helped by the increased pressure from the ice layer and perhaps some lowering of the freezing point from a hopefully not too toxic salt concentration. Ice also supports another intriguing possibility: radiolysis. Ionizing radiation interacting with ice can split water molecules, producing hydrogen and oxidants. On Earth, some deep subsurface microbes do live off hydrogen, produced by water-rock interactions and radiolysis. The Martian radiation environment, while hostile at the surface, could generate chemical energy in protected ice-rich regions. Now, finding this sub-ice life would also require a shallow drilling mission, and the Rosalind Franklin mission may actually find subsurface ice to investigate. But there's also the Mars Life Explorer proposal. If greenlit, this would work towards a mid-latitude lander that'll aim for a location with surface ice. It would have a 2-meter drill, just like Rosalind Franklin, and onboard labs to look for biosignatures and signs of metabolism, both in the borehole and perhaps seeping up from layers of Mars deeper down. Another potential habitat is the Martian lava tubes, orbital imagery has revealed skylights, collapsed ceilings exposing underground voids that likely connect to lava tubes that would have formed billions of years ago when Mars was still volcanically active. These natural caverns could provide excellent radiation shielding and thermal stability. The great unknown here is whether there's water. There could be ice deposits or brines, perhaps even occasional water welling up from below, or they could be bone dry. In the case of lava tubes, we're going to need to send digging or drilling equipment much heavier than any lander or rover can handle. Maybe we just send humans to explore the labyrinthine Martian underworld. What could go wrong? Anywhere close to the Martian surface, water is probably transient and energy is limited. That means we're unlikely to find dense, diverse, or expansive ecosystems. More like sparse, scattered communities that may be dormant much of the time and metabolize and grow at glacial speeds. Just like the Earth microbes that live in sedimentary layers deep beneath the seafloors, with their cell division rates of hundreds of thousands of years. In the case of Mars, going deeper should improve habitability. Just meters down, there's full protection from the worst ravages of the surface. Deeper still, temperature starts to increase. Although the Martian interior is solid to the core, it's still heated by the decay of radioactive material, same as on Earth. Temperature rises by about 10 Kelvin per kilometre. By the time you reach about 6 kilometres or so, it should be warm enough for water to be liquid, if there's any water there. But, intriguingly, recent work published in 2024 used seismic data from NASA's InSight lander to postulate that parts of the Martian midcrust may contain gigantic aquifers, extensive regions of basically groundwater at depths of roughly 10 to 20 kilometres. The interpretation of the seismic data is still debated, but if confirmed, this is potentially the largest region on Mars that could support an ecosystem. The key here is that the seismic data is consistent with aquifers, so water-saturated fractured rock, as opposed to, say, water-carrying clays or solid rock. Water needs to be able to flow in order to not stagnate. Any aqueous ecosystem will reach chemical and energetic equilibrium unless there's a way to maintain chemical gradients for energy and to replenish nutrients and to export waste products. For a deep aquifer, that means the fractures need to connect regions over a sufficiently large scale. Now, we absolutely do have analog life forms on Earth, diverse bacteria and archaea that thrive in deep aquifers, persisting on geochemical energy pathways. If Mars has the right geology, there's no reason that such a deep biosphere should not also exist there. The main issue with this last prospect is that it's going to be enormously difficult to test the idea. It's going to be a long time before we can put together a mission to drill several kilometers beneath the Martian surface. Given the scale and complexity of that effort, this might be something that also has to wait for an actual human presence. Look, we honestly have no idea whether there's currently life on Mars, or ever was, but the implications of extant life would be so huge that we gotta look. Maybe Earth life was actually spawned by hitchhikers on impact ejecta from Mars, or maybe the other way around. Only the discovery of living life on Mars with its intact DNA would tell us that. And if Martian life formed independently of Earth's, well, that tells us that life really does form easily and often, improving the odds that we'll keep finding weird and wonderful life forms as we expand our reach across interstellar space-time. Thank you to The Economist for supporting PBS. From reporting on scientific innovation to the shifting landscape of global politics, The Economist's mission is to deliver comprehensive coverage that goes beyond the headlines. The Economist aims to make difficult topics feel approachable, not daunting, such as a recent feature about America and China's return to the moon and the future of lunar exploration. A digital subscription to The Economist includes daily journalism, plus access to their digital weekly edition, subscriber-only podcasts and newsletters, and Insider, a new weekly video series where senior editors debate the forces shaping geopolitics, defense, economics, and technology. As a viewer of PBS Spacetime, you can get a special 35% off to enjoy The Economist.